Welcome everybody in the lecture hall, welcome everybody on Zoom, welcome everybody from the future. Today we are going to continue with massive parallel processing with a newer technology than Mapreduce. Mapreduce was actually only the beginning of massive parallel processing, and the main idea why it's not enough is that it only has one round of map shuffle reduce, and that's actually not enough for many cases, so that many people ended up using Mapreduce with plenty of jobs, right? For example, for matrix multiplication and so on, if you want to compute the page rank of the web and so on, then that quickly becomes a limitation because you have no way of directly processing more complex queries. And so there was a whole new generation of massive parallel processing tools that emerged. Apache Spark is one of them, but there's many others. The good news is that they all use the same sorts of techniques. It also builds on top of Mapreduce. You see that a lot of aspects of Mapreduce that we covered are actually also applicable to Apache Spark. So this is the technology stack that we have, and now we are in the processing part just to see where we are, and in the coming weeks we'll deal with the upper parts. So we saw Mapreduce looks like this: map, shuffle, reduce, even though for some reason the shuffle part didn't make it to the name, but this is the bottleneck, so map, shuffle, reduce. And we saw that the first version of Mapreduce was based on job trackers and task trackers that are co-located with the name nodes and data nodes and with the HMasters and region servers. The idea is that the task trackers that are executing the map tasks are on the same servers as where the data is, meaning you don't need to ship it over the network or very little of it, and you directly read it as a local disk read. That's short-circuiting. All right. Here's the problem with these first improvements, this first version of Mapreduce. The problem is that the job tracker over there next to the name node has a lot of things to do. It has to do the resource management, meaning knowing the cores, the CPU cores, the memory that there is on every machine to assign the tasks. It needs to schedule the entire job with the map slots, the reduce slots. It needs to monitor for faults. If something crashes, then you need to restart. In some cases, it's enough to just restart a map task that didn't succeed. But if there is a crash in the reduce part and you lose some data, you need to start all over again. So this is why the job tracker has to monitor the whole thing and coordinate all of these, right, to be fault tolerant. This is a huge amount of responsibility for just a single process. This is actually too much. It's actually a bottleneck. One first limitation that the engineers discovered is that you cannot really scale beyond 4,000 nodes. And as soon as you have more than 40,000 tasks or splits, then that starts breaking, right? So we have this scalability issue. Another issue is the bottleneck that, as I said, the job tracker has too many things to do. And if something goes wrong with the job tracker, then the entire thing goes down, right? So this is another aspect. We also say, you know the expression jack of all trades, master of none, right? So the job tracker is trying to do both the scheduling and the monitoring, and it would be ideal if we could split this into different responsibilities. You remember what I explained to you about carefully differentiating between map function, map task, map slot, map phase. This is super important, and I have again a summary here. It's also the same on the reduce side. And the problem, so if you have this in mind, the problem is that in version 1 of Mapreduce, you have to assign the slots before everything starts to either map or reduce. So you have to say this CPU core here will be a mapping, it will be for mapping, and this other one will be for reducing. But what happens is that during the first phase, the map phase, all of the slots, all of the CPU cores that are assigned to reducing, they just don't do anything. It's a waste of resources. They are just sitting there idle until the map phase is complete. And only when it's complete will they actually start reducing. And then it will be the opposite. It will be the map slots that will just be idle while the reduce part is taking place. So this is also not efficient because we are just wasting half of the cluster just idly waiting. So this is a problem that we also want to solve. And this problem was solved. So it's not directly Apache Spark, right? It's like first version 2 of Mapreduce. And it was solved with something called yarn. So when you have a technology, the first letter of which is Y, it very likely means yet. And in that case, yet another resource negotiator, right? So yarn. This technology is actually not just solving these issues for Mapreduce, it can actually be used with many other systems. And the idea of yarn, surprise, surprise, again, the same kind of architecture with a coordinator process that's called the resource manager, and then all of the worker nodes that run the node manager process. But what's specific about yarn is that it gives an abstraction of the cluster with containers. On every one of these machines here, on the node managers, think of it as CPU cores and memory that is divided into containers. And the containers are just sort of virtual machines, if you want to think of them this way, that are available to running whatever you want to run on them, right? Can be Mapreduce, can be Spark, and so on. It's just an abstraction of the resources that there are on the machine. So we have plenty of containers on all the machines, and yarn is basically dealing with allocating these containers to whoever is using the cluster. Right. So the idea now with yarn, the way that this works is that the client submits a job to the resource manager, maybe a Mapreduce job, but we'll see it can be actually not only Mapreduce, but anything, but the job arrives. And then what happens is that the resource manager is not going to take care of the job themselves. No, no, no. They are going to delegate this to one of the containers here that is promoted to an application master. It means that the first node on the left here will be responsible for coordinating the job. And some CPU cores and some part of the memory gets allocated to this. And this is now called the application master. Right. And the application master will be in charge of executing the job, but of course, it's not going to do everything alone. It's going to request help from the resource manager for more containers that are going to be used in order to execute the job. And there you go. Now you have, again, the same infrastructure on the abstract level of coordination by the application master, which is what the job tracker used to do. And the other containers that get allocated, they will do the job of what the task trackers used to do. So we again have this centralized architecture with coordination and worker nodes, except that now the application master does not sit on this machine up there with the resource manager. It's now completely decentralized, right? So this is, who understands this? This is super important because now the responsibilities are distributed. On the one hand, the resource manager takes care of allocating the CPU cores and the memory and so on. But the responsibility of running the job now has been outsourced and decentralized to one of the machines there, the application master. And this is pretty much it. So I will not go too much into the details of yarn. I'm going to keep it on the high level because it's not so important that you understand all the details, but just to give you an idea on very quickly of what this involves. So these containers that I told you about, this is an abstraction of resources, right? It's basically CPU cores, memories, but it can also be some bandwidth for reading from the disk. It can be some bandwidth from the network. Even though typically it's just going to be memory and CPU, right? I think disk and network is work in progress to also make them part of this container abstraction, but typically just think memory and CPU. For example, a container might be 2 CPU cores and 10 gigabytes of memory. That's, for example, what a container could be about. And what happens is that all of these CPU cores and memories, they are managed by the resource manager on the top as application management. And the actual monitoring of the jobs is going to be delegated to the application masters because there can be multiple application masters. It might be that there's 10 people using the cluster at the same time. Alice is running a Mapreduce job. Bob is running another Mapreduce job. Maybe Charlie is running some Apache Spark job and so on. And now you can use the cluster for a company or a university shared across multiple people, right? So we can have plenty of application masters, plenty of people running their jobs. And this is done decentrally by one application master for every person or every job. Okay. So again, very quickly, don't worry too much about the details, but very quickly, just to give you an idea, on the left, you have this resource manager that is the brain of Yarn. And the resource manager is communicating with the node managers that you see on the right. And surprise, surprise, you have exactly the same ideas as we saw in AGFS, these heartbeats that the worker nodes are regularly sending to the coordinator node. So in that case, the node managers send heartbeats to the resource manager just to say, I'm still here. And in the heartbeats, they don't only say, I'm still here, they also say, I have such and such amount of memory, and I have this many cores. And that way, the resource manager knows exactly over the thousands of nodes in the cluster, how much memory there is, how many cores there are, and it keeps track of what is still alive and what's not alive. Because again, if you have thousands of nodes, they will crash. You actually have full-time employees in the data center who run the entire day in the data center, swapping disks and swapping memory sticks. So just so you know that things keep crashing. All right. What's important is that this resource manager, so again, that's the node that is on the top right there. If something goes wrong with Mapreduce or Spark, the resource manager just couldn't care less. It's not their job. They don't care about that. They do not monitor the task. They do not restart anything upon failure. The only responsibility of the resource manager is to keep track of the cores and the memory that there is on the cluster, and upon request, allocate these as containers. That's the only job of the resource manager. It's the application master's job to take care of the monitoring. And this is application specific. There is one for Mapreduce, one for Apache Spark, and so on and so on. And there can be, as I said, multiple of them. All right, now, if there is a problem and something fails, like for example, a map task has just failed and so on, as I said, the resource manager couldn't care less, but the application master is going to notice that, and it's going to restart this map task and relaunch it. Right. So what's important again is that now we delegated the responsibility of monitoring for the execution of the tasks to this application master. All right, now, again, I stay on the high level. The resource manager, whose job it is to allocate the CPU cores and the memory, needs a strategy for that, because there might be 10 people connected to the cluster and they all want to run their jobs. So how do you deal with that? How do you allocate the cluster? A first strategy is to say, okay, first come, first served. Alice comes first, okay, you get the entire cluster to yourself and you can use it. And once you're done, Bob will get it. Bob will then get the entire cluster and so on. This is called FIFO, first in, first out. You just queue the people and everybody gets the full cluster, but one after another in turn. That's the first strategy. It's naive, but it works. Another strategy is to have some hierarchy in the usage of the cluster. Now, this is political. This is not technical. It's political. There's going to be, for example, in a university, the executive board, and then the departments, conferences, and so on, who decide. And they are the ones who pay for the cluster, for all these nodes and so on. And so they are going to decide, okay, the math department is going to get 40%, and the physics department 10%, and the computer science department 50%. Maybe that's at the level of the executive board. And then at the level of the departments, again, there's meetings, and then political decision again. In math, they decide, okay, 20% goes to the analysis people, and 80% goes to the algebra people, right? And then in CS, we say, okay, 20% for the theoretical computer science, 80% for the database people, for example. And then if you do the math, it's just a multiplication of the overall cluster. It means that 10% of the entire cluster will go to theoretical computer science, 40% to databases, and so on. Again, that's just a political decision. Once you've made this decision, you just enter them into Yarn, and Yarn will make sure that somehow this is enforced, and that the cluster will be used in that way. But the difference with this is that now it's not like somebody has the entire cluster. Now you're going to share the cluster, right? And so you're going to have half of the machine roughly for computer scientists, 1 in 10 for physicists, and so on and so on. All right, for whom is that clear? Okay, again, that's a political decision. And then the technical aspect is how do you actually now distribute it in that way? And the way you do that is that once you have this decision made, you can have different queues in the cluster, and according to the decisions that were made on the percentages, you just allocate all of these resources, but within a queue, you then do it FIFO again, right? So within analysis, within algebra, within theoretical computer science, it's all FIFO. Everybody has the whole 8%, the whole 32%, the whole 10%. That's called the capacity scheduler. And then there is the fair scheduler, and I'm not going to annoy you with the details. I used to actually, but it can be very complex, very easily. Just on a high level, what does the fair scheduler do? It just optimizes, because imagine that during 1 month, there is a big algebra conference and everybody's out of the university and the cluster is just sitting idle with nobody using it. What do you do in that case? Well, it would be sad to just waste this cluster completely unused. So the fair scheduler is going to reallocate unused resources fairly across everybody else, right? So that means that, for example, here, imagine that no mathematician or physicist is using the cluster, then the theoretical computer science will not get 10%, but 20% of the whole cluster, right? It's just a fair reallocation of what is not unused. And when people come back, then they again slowly get back the resources that they deserve. Okay. Here, I'm always wondering, should I actually annoy you with these details or not, or should I not? But don't worry, it's not at the exam or anything. It's just so that you have an idea of the challenge. I just want to show you it's not that easy. The reason it's not easy is that, okay, if it's one dimension, it's easy, right? Because if you have, for example, here, imagine you have 100 terabytes of memory on the cluster, and you just care about memory. So if you have 100 terabytes, that's easy. The analysis, they will get 8 terabytes, algebra 32 terabytes, physics 10 terabytes, TI 10 terabytes, and database 40 terabytes, right? In that case, it's easy. The problem is that there's 2 dimensions here. There's not only the memory, there's also the CPU cores. And people might not be using the memory and the cores in the same way. For example, Alice might need for every one of her containers, 3% of the memory of the cluster and 2% of the CPU. So it's more memory intensive. But Bob only needs 1% of memory for every container, but 6% of CPU. So the ratio of usage between the memory and the CPU is not the same for Alice and Bob. So the question is, how do you allocate that fairly between Alice and Bob? How do you determine how many containers Alice is getting and how many Bob is getting? And turns out that was actually solved by the same people actually who are in the Spark team. So it's somehow between Berkeley and Stanford, all of this work, and that's called dominant resource fairness. And the idea here is to look at the dominant resource. For example, in the case of Alice, if every one of her containers using 3% of memory but 2% of GPU, then it's the 3% that wins. So you focus on the 3% for Alice. And for Bob, it's the opposite. It's less memory than CPU in percentage, so you focus on the CPU. So if you only look at the maximum percentage on each side, that's 3 for Alice and 6 for Bob. So it kind of means that Bob's containers are twice as big as Alice's containers. So that means that if they have 50-50, that's the policy here at the bottom, if they each get half of the cluster, then you probably agree that Alice should get twice as many containers as Bob, because they are twice as small. Who agrees? Right? It's just logical. But again, the trick here is that we ignore the non-dominant resource. So we ignore the CPU for Alice and we ignore the memory for Bob. And we just say, okay, Bob's containers are twice as large, so Bob gets half the number of containers, and then things are fair again, 50-50. Okay, that's called dominant resource fairness, and that's the sort of things that are going on in the resource manager to take care of this, right? So in that case, Alice is going to get 20 containers, and Bob is going to get 10 containers, and you see they both get 60% of the cluster in whatever they are interested in. Alice gets 60% of the memory, Bob gets 60% of the CPU. Okay. Now, I said I'm not annoying you with more details. Just to tell you that this yarn thing works with plenty of technologies. Mapreduce is one of them. It also works with Apache Spark. That's the DAC distributed processing. That's not as scary as it sounds. I will show you. There's also message parsing interface. I think that's for the high performance computing people, weather, climate, and that sort of things, and graph processing, and so on and so on and so on. So you can actually use Yarn with whatever technology you want, as long as you have this concept of coordination by the application master and then the work done by the other containers. Okay, so as a summary, what Yarn brings us is version 2 of Mapreduce. It's a newer version that cleanly separates between scheduling and monitoring. Scheduling is still done centrally by the resource manager, but the monitoring of one job is delegated to one of the containers that is an application master. It's more scalable. It actually leads to bigger jobs. It's more available, and it's multi-tenant, meaning you can have 10 people or 100 people or 1,000 people at the same time using the cluster and sharing the cluster. In fact, the goal of the companies when this was developed is to avoid wasting resources and maximize the usage of the cluster, right? Okay. That's it for Yarn. And again, I stayed on the high level. I just was very high level about it. I used to actually give more details, but there are several reasons why I stopped doing that first. As soon as you get into the details, it's not always well documented, and you will have divergence of explanations on the resources in books, on the internet, in the documentation, and so on. So that was very confusing. And in fact, especially for big data for engineers, what you are here to learn is how to use the system, how to use Mapreduce, how to use Apache Spark. So these considerations on the scheduling and so on is secondary if you do this. Okay, so this is why I'm already done with Yarn. It's barely been 20 plus minutes, and now I move over to Spark. Any questions so far on Yarn? Yes?
Yes, so in the context of like job and task allocation, I think there are a lot of like constraints with that, especially since you mentioned last time that you try to bring the query to the actual worker node. Is that in somehow influencing the decision where certain jobs are being allocated?
Yes, this is an additional challenge. So if I correctly understood, you mean that the data on HDFS, the blocks are going to be on specific machines.
Yeah.
And so when the application master requests containers in order to read that data, then it should also be ensured that this is on machines that actually have a replica of the block. Yes, this is absolutely true. And that's also part of the challenge of the whole thing. It's just that if it fails, meaning that you allocate a map slot that is executing a map task for data not on the same machine, it's just going to be slower. It's not like it will not work, right? It's just going to be slower because then you ship data over the network. But ideally, the job of the resource manager is to avoid this happening and make sure that as much as possible, the data should be sitting on the same machine as where it is processed. Yeah, so this is absolutely correct.
Thank you.
Yeah, thank you. Very good remark. Okay. So now, no other questions, right? Okay, now let's move over to the cool stuff. So, introduction to Spark. First, a provocative slide. Mapreduce, I said, is you map, then you shuffle, then you reduce. Let me claim that reducing is actually the same as mapping. Why? It's just something that runs in parallel, right? So you could caricature it and call it map, shuffle, map, right? Because in the picture, is there any difference between the map phase and the reduce phase? No, just in parallel. So map, shuffle, map. This is actually very specific. It's a very constraining and limiting way of looking at how data is queried. Can we generalize that in some way? So from this, where we have some inputs that we map to some intermediate data that we reduce to some output data, the answer is yes, we can. And all that means is that instead of having this very limited way with just input, intermediate, output, we generalize that to any topology, any structure here that basically tells you how the data flows. But there is one limitation though, and only one. There cannot be cycles. It's kind of logical, right? Because this is basically a dependency graph, if you want. This is the dependency that every intermediate data depends on some other intermediate data. For example, this intermediate data depends on that intermediate data and that intermediate data, right? So there is a dependency. But imagine if there are cycles, you cannot resolve them. If there is a cycle, then A needs B, which needs C, which needs A, so you cannot do anything, right? You cannot start anywhere. So there cannot be any cycle. And the computer scientists, they have a name for these graphs that don't have any cycles. This is called the DAG, directly acyclic graph, DAG. So a DAG looks exactly like that. It's just some dependency graph. If we have, do we have any physicists? Okay. If you just think of special relativity, causal models, and so on, this is also the same structure. In causal models, you also cannot have cycles, right? You cannot go back in time. Okay, so Spark does exactly that. Spark generalizes this concept of first mapping, then reducing to any DAG of dependencies between the data, and this is how it works. Now, a bit of terminology. In Mapreduce, you remember that everything is a collection of key-value pairs. The input is a collection of key-value pairs, the intermediate data is a collection of key-value pairs, the output is a collection of key-value pairs, everything is a collection of key-value pairs. In Spark, the equivalent is called an RDD. It's a resilience distributed data set, but we just say RDD. And we'll see it doesn't need to be a collection of key-value pairs. It can be a collection of whatever you want. It doesn't have to be pairs. Just think of RDDs are a big collection of whatever, as a big collection of whatever. This collection obviously is going to be partitioned, because if we want to have collections that are petabytes or exabytes large, then you need to partition them for them to be stored across machines, right? So it's a collection of whatever, and that collection is partitioned. Now that shouldn't surprise you, because we spent the first few weeks of the lecture partitioning everything in chunks, in shards, in splits, in blocks. There are so many names for that. So that shouldn't be a surprise anymore that we do that sort of things, right? So we just partition the RDD. So again, the RDDs are a big, I should even have said huge, enormous, gigantic collection of whatever. Okay. So now, in order to use Spark, and I'm still on the logical level here, what do we do with these RDDs? Well, first you create them, then you transform them, and then you act on them in order to obtain the final results. So how can I create an RDD? Well, from many different sources. For example, my RDD could come from HDFS. Maybe on HDFS, I have a petabyte large file that is full of JSON lines. So that would be an RDD that is a collection of JSON objects, right? Maybe it has trillions of JSON objects, and I just read them from HDFS. So maybe it's a single big petabyte file, or, as is more common, maybe it's a directory on HDFS that has 1,000 files in it. These are the shards of the data sets, and every file contains 1 billion. So if you have 1,000 files with each 1 billion objects, that's again 1 trillion objects. So can come from HDFS. Of course, it doesn't have to be JSON. It could be text, it could be Parquet, it could be whatever you want, right? But basically, whether it's JSON files, whether it's Parquet and so on, it's always a collection of whatever. Everything can be seen as a collection of whatever. Now it can come also from the local file system. Of course, it's not going to be petabytes then, but you can also create an RDD right there from your laptop, right? Where this laptop right here can create an RDD, and then you can start working with this RDD, maybe map it to something bigger and so on. So it can come from the local file system. It can come from S3. It's also compatible with Amazon S3. So maybe you have these petabytes of data of JSON objects sitting on S3. Azure Blob Storage, Google Storage, and so on, Google Cloud Storage, anywhere, or even on the fly. You can even create RDDs just like that, just creating and making up values, just creating an RDD. So all of that can be used in order to create an RDD, which is basically the input to the whole system. Then you can transform an RDD into an RDD. You already know two examples of that. That's map and reduce, right? You can map an RDD to another RDD. You can reduce an RDD to another RDD. Of course, in Mapreduce, it wasn't called RDD. It was just a collection of key value pairs, right? But this is the idea. You were mapping a collection of key value pairs to another, or reducing a collection of key value pairs to another. Now we have a fully generic architecture where we transform RDDs to any other RDDs, but even transformations are generic. It doesn't need to be mapped, doesn't need to be reduced. In fact, it's like a restaurant menu that you pick from. Right? So I'm gonna show you actually the menu of things you can do on RDDs. It's a very, very rich set of transformations. And when you are done with this DAG of transformation that you can organize in any way you want as the user, when you're done, you can say what you want to do with the results. If the results are small, maybe you can just print them on screen. Maybe you wanted to know the 10 most frequent words in a petabyte text corpus, but 10 words, that's small enough that you can just print it on your screen. So printing on your screen is a possibility. Another one, if it's small enough, is to store it locally on your hard drive. So you download it, maybe it's just a megabyte of data, then you just download it from the cluster and store it on your drive. Or maybe the output is very large. Maybe the output is also a petabyte of data. Not a problem at all. Then you just direct it to HDFS or S3 or Azure Blob Storage. This is called an action, right? So creation, transformation, action, right? And we will see, especially transformation and action, there's a whole restaurant menu full of things that you can pick from. Any questions so far? Right. So again, I say again, an RDD is a huge collection, petabytes, can be petabyte, exabytes of whatever you want. Pairs, but doesn't have to be pairs. Okay. So now that we have that, I have again this graph, and now I put RDD on every node because now we know that they are called RDDs. And you can see how every collection of whatever is computing from other collections of whatever in this DAG. And lineage graph is just another word for that tag. Okay, so now what happens if you go ahead and write code in your Jupyter notebook that creates an RDD, that transforms an RDD into other RDDs? What happens? Well, the answer is nothing actually happens, because it's called lazy evaluation. Nothing happens because there is no action in there. So if you just go ahead and write transformations, you're only expressing intent, but you're not actually doing it. The real action happens when you have an action. So once you have an action there, this is when it triggers the whole thing, and then the cluster goes into motion, starts computing stuff and spitting out the results to your screen, right? This is called lazy evaluation by computer scientists. It means you only start evaluating when you actually need what you need to compute. Lazy evaluation. Okay. Now, more practically, how do you use Apache Spark? The native language of Apache Spark is Scala. Who heard of Scala? Nobody. It comes from EPFL. Some of you did hear from Scala. Scala is kind of a cousin of Java. So Scala also runs on the Java virtual machine. So it's exactly the same execution engine. It's just another language that looks different and has many productivity optimizations. So it grew a bit in popularity in the past, I would say 10 plus years. So Scala and Java are kind of cousins. Mapreduce, Hadoop Mapreduce, HDFS and so on was all implemented in Java, and Spark is implemented in Scala. But since they run on the same virtual machine, it doesn't really matter because you can also use Java very easily for Spark because it's on the same machine. Python also works, but Python is more involved, not as a user, right? But is more involved to design for the engineers who design Spark, because Python does not run on the Java virtual machine. And so what you will notice if you try to use Python with Spark is just that it's a bit slower because there is a bit of an overhead to make it work, but it works. And actually the Python usage of Spark is also called PySpark. That's also a popular name that you will see. Now, Where do you write, for example, PySpark? Well, you can write it in the Jupyter notebook, just like we've seen it many times in the lecture. So you can just go ahead and write your creation and transformation and action just using Python, and it will just work. In Java or Scala, typically you will need a development environment. You can start writing a Java application that's just going to use the Spark API, application programming interface, to orchestrate some job on Spark. There is another alternative yet, which is the shell. You can also open a shell on the command line, and then you type what you want to do. You have a PySpark shell, and then you can just go ahead and write some Python. You have a Scala shell, and you can just go ahead and type some Scala, and that works as well. It's just less fancy than the Jupyter notebook, but it works as well. Okay. But let me give you a concrete example just so that you have the feeling of this. So, if I correctly remember, that should be Python. I used to do it in Scala, but I think I converted it to Python just because we use it in the course. But this is a very simple example. So, I'm going to create an RDD, but just for the purpose of the example, that's not going to be data that I found on HDFS or on the disk. I'm just making it up on the fly. So it means that I just built some array, hello world, hello there. It's an array of 2 strings. And I just ask to build an RDD out of that. So it's going to be not a huge collection. It's a ridiculously small collection of just 2 things, 2 strings, but it's still an RDD. And the way I create an RDD is with the parallelize function. The parallelize function is called on this SC, that actually means Spark context. So anytime you want to use Spark in the Jupyter notebook, you have to create a Spark context, just usually already there, and you just click and execute it. And once you have SC, then you call parallelize, hello world, hello there, and store it into a variable called RD, excuse me, RDD1. All right. So does anything happen at that point? No, there is no action, right? It's all lazy. So all I express here is an intent to build an RDD with RDD1. So that's why I put the dashed line around this depiction of the RDD, right? Hello world, hello there. Then I create another RDD, this time with a transformation. So this transformation in this case is called the flat map. It's one of the hundreds different transformations that you can do. And here I have this seemingly complex thing. It's called the lambda. What does that mean? You remember that in Mapreduce, when I have the map phase, I need to supply a map function. And for the reduce phase, I need to supply a reduce function. So I need to give a function. It's the same here. If I do a flat map, I also need to supply a function. That function tells me how I'm mapping the input to the output. It's a function. And lambda is just a popular name in computer science for when you supply a function on the fly. It's called a lambda. It's for historical reasons. So what is this function? It's almost math here. It just says that if the input is value, then the output of that function is the split of the value in, using spaces. So it basically means that hello space world is going to be mapped to hello and then world, because there's a space right there. So you just because you split here, just means you the other side. You split here with the space and split here with the space. So hello world will be mapped to a sequence of 2 strings, hello and world, and this one will be mapped to a sequence of 2 strings, hello and there. And since it's a flat map, it's just flattened again, right? So hello world, hello there. So again, that's just a fancy way of supplying my map function, saying I take a value and I split it based on the spaces. What happens here? Again, nothing. It's just lazy evaluation. So at that point, nothing actually gets computed. I only put in the bottom of the screen here for pedagogical purposes what the intent is, but nothing is actually yet computed. I need to again click so that my clicker works. Now. So now is an action. The action is called count by value. I'm just counting how many I have of each. So hello, I have 2 of them, hello, comma. World, I have 1, and there I have 1. Now you notice that the dashed lines are gone. The dashed lines are gone now because that's an action. So now I'm actually triggering the computation. And then on your Jupyter notebook, you will see this output right there with these 3 pairs key value. It turns out that in that case, the output is a collection of key value pairs. But again, it doesn't have to be always, right? But in that case, it is a collection of key value pairs. Okay. Who understands what's going on? Okay. So what I'm going to be doing basically for the next maybe half hour or 40 minutes is that I'm just going to go through the menu and show you everything that you can do with Spark. So not just flat map and count by value and parallelize, but everything else that there is. Any questions so far? Okay. All right. Now that should be relatively easy, so you can just sit and look because that's just going through a menu of things. So I'll start with transformations and the ones that are just mapping one collection to one collection, and it doesn't need to be pairs. So this is really the easy part. I have 5 minutes to the break. Okay, so they all look like this, right? They take an RDD, so they take a collection of whatever, and they turn it into a collection of whatever. So here's the first transformation. It's called filter. And what it does is, according to its name, it's filtering things. So if you want to filter a collection, you need to supply a function, a filter function, and that's a yes-no function. It takes as input an item. I'm going to call an item all of these things that they are in the collection of whatever. So I'm not going to be saying collection of whatever. I'm going to be saying collection of items, just more formally. So the function that you supply here must take an item and tells you yes or no. Yes, I keep it. No, I don't keep it. And what the filter transformation is doing is that it's evaluating this filter function on every one of the items in the input side. And it's only letting through those for which the function said yes, and those for which the function said no are just out. Right? For whom is that clear? That's an easy one, right? So you can filter things. What relational algebra operator can you easily implement with this? Imagine that the items are actually rows, that this is a table that is a collection of rows, and you want to filter the rows. What relational algebra operator is this? Remember? Anybody knows on Zoom? If we filter rows in a relational table, start with an S. Yes?
Selection.
Absolutely. So you can implement with the filter transformation, you can implement a relational algebra selection. Who sees that? Okay. Super easy. Okay. And then the function, the yes-no function, is just the selection predicates that you would have in the where clause in SQL. So you see here the intuition that you already see some SQL implementation in there, right? And it is actually true that Apache Spark can actually be used as some way of implementing SQL, but on very large scales. So you see why it was useful to learn SQL. All right, but let's stay at the low level for now and not go to SQL just yet. So a filter transformation that outputs a subset of the input based on a yes-no function. Here's another one. This is a map transformation. A map transformation also needs a function. It's a function that takes an item, returns an item, right? So it's that simple. And so each item of the input is mapped to an item in the output. Okay. Now, be careful. This is in fact not the same as the map in Mapreduce. The same as the map in Mapreduce is actually the flat map. And the idea is very simple, is that in Mapreduce, you might remember that the map function of Mapreduce can output 0, 1, or more key values. You remember that, right? 0, 1, or more. But in that case, the map function, it's only 1. So this is why this is not the Mapreduce one. But the flat map gives you that, because in the flat map transformation, the flat map function can output 0, 1, or more items, and then it's all flattened. when you get your output. So this is in fact the equivalent of the Mapreduce map site. But there is one difference with the Mapreduce map site is that in Mapreduce, it's key values everywhere. Here, it doesn't have to be key values. It can be anything, right? So this is why I say item. You take an item and return 0, 1, or more items. So this is the flat map, and that's the same one that we saw here, right? The flat map is the same one. Okay, who is with me? That should be easy, right? Who is with me? Okay. This is just a menu. We just go through what we can do. And it's the break. I see it's already 9. So let's take a break. And then in the second hour, again, I will continue to go through all these transformations and actions. And then we'll move over to Spark SQL and data frames and do many other interesting things. So I'll all see you after the break in 15 minutes at 9:15. Thank you very much.